Hi everybody, Physics Ninja. Today what we want to do is look at the induction of two objects. We're going to consider first a solenoid. That's probably the easiest case to consider. And then we'll consider a toroid. So a solenoid is just a cylinder and we've wrapped wire around it a certain number of turns. And a toroid is basically, it could have different shapes, but one is like a donut. But the cross section could either be kind of rectangular or circular, kind of depending on the geometry of the object. All right, we're going to show you how to set up the equations and how to solve for the induction. Since it's only one object, we're really talking about the self-inductance of this particular object. Okay, like with all my videos, if you like it, give it a thumbs up. The best way to support Physics Ninja is to subscribe to my channel. All right, let's get started. Okay, so to calculate the self-inductance of a solenoid, you have to start with our definition, which is the number of turns multiplied by the magnetic flux through one of those turns and divided by the current I flowing through. Okay, so it really boils down to if we can evaluate what the magnetic flux is, then that's it. We just plug it into our equation and we're going to get the inductance. So let's go ahead and remember our definition for magnetic flux. Magnetic flux, again, if I have a magnetic field that varies in space, it looks something like this. However, for our solenoid right here, since B is going to be a constant value, I'll show you how to calculate that in just a minute. If B is a constant value, this equation over here will simplify because it means I could take it out. So you're left with B multiplied by the area and multiplied by cos of the angle between kind of both of those vectors over here. So in this case, actually we don't have to worry about cos of the angle theta because this is what it looks like. We have magnetic field, which is basically only inside and it's pointing to the right. And if I consider the area here to be the area of one of these turns, you can see that that area vector also points in the same direction. And therefore, the angle theta is actually 0 and cos of 0 equals to 1. So don't worry about that. So let me go ahead and just redraw this circle over here because we have to consider a certain geometry. And what I'm going to consider is that this is a circular cross section and the radius is going to be r. And the reason I need that is because we need the area in order to calculate the flux. And the area of a circle is very, very straightforward, simply pi r squared. Okay, so all we're really left with now, if you think about this equation for the flux, it boils down to evaluating what is the magnetic field B. So in order to do that, what we're going to use is Ampere's law. Yeah, if you don't remember Ampere's law, don't worry, we'll write it down here. Ampere's law says that if you integrate the magnetic field over a closed loop, okay, that has to be equal to, in this case, it's air-filled, so it's mu0 multiplied by how much current is actually enclosed by that loop. So let's go ahead and draw an Amperian loop for this problem. So I'm going to draw a straight line that goes like this. I'm going to draw a rectangular line, basically, that has to form a closed loop. And this is going to be the direction that I'm going to integrate. Now, for this solenoid, again, although the field, you can see the field lines kind of going out, and there's a little bit of field over here, the approximation, which is actually a pretty good approximation, is that the magnetic field is really small outside of the solenoid. And basically, the majority of those field lines are contained inside the solenoid. So that means that this magnetic field here is basically a constant value inside the solenoid and 0 everywhere else. Now, the reason that's useful is because it really simplifies this left-hand side of Ampere's law because we no longer have to worry about integrating outside because the field is 0 there. So all you're left with for this kind of complicated integral is the magnetic field B, which is a constant, and multiplied by the length, right? Multiplied by the length in this case is little l. Okay, and that has to be equal to mu0. Now, how much current is actually enclosed by this Amperian loop? Again, I have a solenoid here that has n turns, right? And I'm including all of those turns inside this loop. So that means that the total current here has to be n times multiply the current through each one. All right, all you have to do now is rearrange my equation. And I have that the magnetic field inside the solenoid is mu0 multiplied by n. I'll bring the L down here at the bottom, and then multiplied by the current through each one. Okay, so this is really important for this problem. All right, there you go. So this term here in the brackets is the number of turns per unit length. Okay, so let's go ahead now and substitute this inside our flux equation. And once you have the flux, you simply go back to the inductance equation. All right, so we should be able to do this in 2 steps here. So the flux is this. We have mu 0, we have n over little l, we have the current, and then we have to multiply by the area, which in this case we said was pi r squared. Okay, and now the last step is the inductance. So I'm going to group together. Notice there's an n here in front, and there's another n over here. So you're going to have an n squared term. N squared. Now look what happens. I have current in the flux, and I have a current here in the denominator. Those things will cancel out. So the inductance never depends on the current. Let's go ahead and do this. Divided by this little length here, L. And what else am I left with? I'm still left with the area. The area was pi r squared, so you can't forget about that term. Let's go ahead and write this. Pi r squared. Okay, so there is the expression here for the inductance of a solenoid. Notice that it really depends on what is inside the solenoid, right? It really depends on 2 terms. Inside, that is basically if it's air-filled, we have a mu 0. If you have something else, for example, if I have iron inside, then I replace the mu 0 with the permeability of iron, which would be, say, approximately 200. Multiplied by mu 0. What else? All of the other terms here depend on the geometry of the object. Okay? Oops, geometry. I have to remember how to spell that one. And if you have a look at it, it's the number of turns. It's also the length, and also what is the radius of each one of those turns, right? These are all geometrical terms. Okay, so this is really, really important. Let's take a numerical example now. All right, so we consider that the length here is, let's assume it's 10 centimeters. What else? The number of turns. Let's set n equals to 200 turns. Okay, and we're going to have a radius. The radius r. Let's maybe just set that to 1 centimeter. Okay. When you start substituting the numbers in here, again, we want to convert things into meters, okay? Because at the end of the day, if you plug in all our numbers over here, this is what we get. So we get a mu 0 is 4 pi times 10 to the negative 7. Okay. N now is going to be squared, 200 squared. Pi, we can use that with the calculator. R is 1 centimeter. We have to square that one. And now divided by the length. And the length is 10 centimeters, so 0.1. All right, if you substitute everything in the calculator, and assuming I did it correctly, I get 0.000158. And that there is measured in henries. We use the letter capital H in order to measure that. And again, if you want to just maybe convert that, get rid of some of those zeros, you can write it as 0.158 millihenry. Okay, so that would be the value of the self-inductance for this solenoid with this particular geometry and with air inside. All right, I used the permeability of free space here. Okay, let's go have a look now at the toroid. All right, so for the next case here, we have a toroid. Here is kind of just a picture of what it might look like, right? You simply have a copper wire that's wound around, in this case, kind of a donut-shaped object, right? And again, sometimes the core here is made of iron, right, to give it some stability or some structure so you can wrap the wire around it. If I take a cross-sectional view, again, depending on the shape of the object inside, sometimes you have a square cross-section, right? You could also have examples where you have a circular cross-section instead of a square. Okay, so I'll show you kind of an approximation to deal with the circle in just a minute, but let's start with the square. The square is pretty easy to calculate. You can do it analytically and without taking too much time. All right, depending on the orientation of the current over here, again, if you take a cross section in the opposite direction, not like this, but kind of slicing it along the half point, what you will look like is something like this. Okay, so the current is maybe coming out of the page on the outer part of the torus, but it's going into the page on the inside, right? So now if you consider the direction of the magnetic field produced by these types of current, in order to do that, you have to use kind of a right-hand rule. But one direction could be the clockwise direction as shown here by these green lines, okay? The other thing we need to know is, well, what is the size of this toroid? Okay, so for us, we're going to consider something with an inside radius here, which is equal to A, and an external radius here, which is equal to B. All right, so let's go and start the calculation based on this geometry right here. And we're going to apply the same formula that we did for the solenoid. All right, so what we're going to first do is calculate what is the magnetic field here inside this toroid. Each turn has a current I, and we're going to assume here that we have n turns. If you have a look at the sketch of the magnetic field lines inside the toroid, you can see in this case they form clockwise circles over here. So what we're going to do for our Amperian loop here is our Amperian loop is going to be inside, and we're going to try to, oh, that's a bad looking circle. Let's try that again. Sometimes you got to go a little faster if you're trying to draw a nice circle. I am horrible at circles, but there's my Amperian loop. The Amperian loop here is going to have a particular radius. Let's just call it little r. And let's go ahead and calculate the magnetic field using Ampere's law. Again, Ampere's law, if you remember, B dot dl equals to mu 0 multiplied by I enclosed. All right, the right-hand side of Ampere's law is always the easiest to do. It's mu 0. How much current is enclosed? Well, if you have a look, I'm enclosing all of these turns over here. I'm enclosing n turns, so that actually looks the same thing as the solenoid, right? N multiplied by I. Each turn has a current I flowing through it. All right, now for the left-hand side of Ampere's law. Again, if I'm a certain distance away from the center of the toroid, in this case here, the magnetic field, actually the magnitude here, is going to be a constant value. Okay, so this guy here basically simplifies, because I can, if anything is constant, I can take it out of the integral. What I'm left with now is simply integrating around this Amperian loop, and for a circle, that is simply the circumference. So it's going to be 2 pi multiplied by little r, okay, equals to mu 0 ni. Okay, notice again, for a toroid, there's very little magnetic field outside of the loop. Okay, so I'm really just enclosing only the n turns inside. So now we would just rearrange my equation. What I have now is my expression for the magnetic field. It's a little bit more complicated than the solenoid. One thing you can see is that the field depends on the distance from the center, right? So that means that the field is bigger here than it is on the other side of the toroid. Okay, so that was a little bit different. So we don't have a constant value anymore. We have a larger field if I have a smaller point of evaluation. So that would mean, for example, if I look at the picture above, if I'm evaluating the field right here versus on the opposite side, I would have a bigger value for this radius than I would for the outer radius of the toroid. All right, the next thing we want to do now is calculate the flux. And then we can use that to calculate the self-inductance. So let's go on the next page and finish this off. Just like we did for the solenoid, we have to calculate what is the magnetic flux now. Okay, again, the magnetic flux is the field integrated over the area. And the area that I'm considering, again, if this has a rectangular cross-section, is going to be this area right here. Okay, we have a height h, and we have to evaluate the field everywhere inside this area, but the field is no longer constant. So we actually do have to integrate. Again, we don't have to worry about any direction between the field and the area vector here that is kind of perpendicular to that plane, because they're in the same direction. Okay, so at the end, this really boils down to b integrated over the area. So let's go ahead and set up this integral here. So we have that our flux is equal to, we'll substitute the expression for the magnetic field, and we're integrating over two variables, right? We're integrating, say, from 0 to the height h, And we're also going to be integrating from A to B. All right, the magnetic field equation is what I had on the previous page. Go ahead and substitute that, mu 0, n I over 2 pi r. The area now, if you think about what the area is, again, I'm looking at an element of area. An element of area is going to have a thickness over here, dr, and it's going to have a height, dz. Okay, we can take out all the constant terms because we don't have to worry about those from the integration. So let's take out all the constant terms. We get mu 0, we get n, we get I. Man, almost all the terms are constant. 2 pi you can take out, and now everything boils down to integrating from 0 to h and a to b. And the function here is just 1 over r over dr dz. You can see that this term here doesn't depend on z, so that's very easy. That's simply going to give us h. And now the integral of 1 over r, if you remember that one from your calculus class, that equals to the natural log. Okay, so let's go ahead and do that. So mu 0, ni, 2 pi, those were all our constant terms. The integral over dz boils down to simply multiplying by h. And the integral right here is the natural log of r, and that's evaluated between those limits, a and b. Again, if you substitute those limits in there, I can just go ahead and just do that right away. What you're left with is b over a. Okay, and those are simply the inner and outer radii of this toroid. Okay, so this is really our final expression over here. It's a little bit more complicated than the solenoid case, but it's not really that bad. Guess what? Now we're in a position to evaluate what is the self-inductance because we just apply our formula. We have the flux. So all you have to do is multiply the flux by the quantity n and divide by the current. So I write down the final expression now for the self-inductance of the toroid, mu 0. Let me divide by 2 pi. Okay, the n becomes n squared. I don't have current anymore because I've divided through by current. And then I'm left with this term and then the natural log of b over a. And that's it. All right, that is our final equation. Again, I've actually done this calculation and included all the terms, right? I haven't really approximated the integration, right? Let me go on another page though, and I want to show you what sometimes people do is instead of a rectangular cross section, many times you may have a circular cross section because your toroid might be just like a donut. Okay. In that case, sometimes this integral would be quite difficult to do because the field would be different at different points along this circular cross section. But you can approximate that. Now let me show you how to do that. And like I said, in some cases, your cross section here might be circular. And evaluating the integral to get the flux is not as easy because you have to integrate over this whole circle and the field varies as a function of the distance, right? So it's a little bit more complicated, but some cases you might not want the exact result, okay? You might just want an approximate value for the inductance. So what you can do is just, instead of really evaluating what the true flux is, what we're going to assume here is that the magnetic field is more or less uniform everywhere here. Now that's not true, but let's just take the value at the center of the circle over here. Okay, so we're going to use that for our flux over here. So if I substitute that, okay, the flux now is simply going to be the magnetic field, which we're going to take right up here. Except instead of integrating it, what I am going to do is I am simply going to take the value at the radius of this torus. Okay, that's what little r means right here. Now what else? To get the flux, I also need to multiply by the area of the cross section. So now if the area has a radius big R, then that here simply becomes pi r squared like this. Okay, so capital R is the radius of the cross section. Little r is the radius of the toroid. All right, we can simplify some of the terms here. The current always cancels out. All right, and you can get kind of to an approximate value of the inductance, and it looks something like this, mu 0. It still has some of these terms, right? N squared is still there, but all the geometrical terms now look a little bit different. We simply have a r squared over little r, okay? And that would be an approximate value for the self-inductance, okay? Anyway, that's it for this particular video. Hopefully you kind of get a better feeling on how to calculate the inductance. You can see how it could quickly get really complicated, especially with all of these kind of different cross-sectional values, with the magnetic field not being uniform over that cross-section, right? The flux calculation becomes more complicated. All right, thanks for watching, folks.